Hello, welcome to today's lesson on section 8.3. I apologize for making this video later than I had planned. My laptop was giving me some problems, so I had to back up my files, just in case if the laptop crashes. So let's start. So here's a general way you can write a rational function. So A is the leading coefficient for your numerator, and B is the leading coefficient for your denominator. M is the highest exponent for your numerator, and N is the highest exponent for the denominator. Usually we tend to call the highest exponent the degree, which I think is a term we've used in this class before. So there's three cases to consider. Case 1, when m is less than n. Case 2, when m equals n. And case 3, when m is greater than n. Give you some examples of each. If I have y equals x over x squared plus 4, clearly m equals 1 and n equals 2. So we see that m is less than n. Example of the second case would be something like this here. X squared over x squared plus 1, m equals 2, and n equals 2. And case 3. Set x squared over x plus 1, m equals 2, and n equals 1. The first case I like to call bottom heavy. That's because the bottom of the fraction has a higher exponent, or a higher degree, than the top function. The third case I like to call top heavy because the numerator has a higher degree than the denominator. And I don't really have a special name for the second case, just when the degrees are the same. Now let's see what happens with each case. So for case 1, m is less than n. What's going to happen is that your horizontal asymptote will be y equals 0. And here's the reason why. And this is always true. Let's say you have x over x squared plus 4. If x gets large, meaning x is approaching positive infinity, y will approach 0. If you don't believe me, plug in numbers. So if you were to punch this in your calculator, so you might want to pause the video and get a calculator out. But if you did 100 divided by 100 squared plus 4, I think you get 0.009999. If you repeat the process and plug in 1,000, so you have 1,000 divided by 1,000 squared plus 4, the calculator should say 9.99996 e negative 4. What that means is it moves the decimal place 4 places to the left. So it's actually 0.000999, a whole bunch of other 9s. And the more you make x bigger, the more likely y is going to get closer and closer to 0. So just the way it behaves. The graph will basically, or the y values will go towards 0 when x gets large. Same is true if x gets small, meaning x is approaching negative infinity. Same thing will happen. So again, if you plug in large x values or small x values, y approaches 0. Now for case 2, if m equals n, your horizontal asymptote will just be y equals a divided by b. Again, if you were plugging numbers, large numbers into this here, we will see for ourselves, because the a value is 1 and the b value is 1, that's the coefficient for both x squares. The ratio is y equals 1 over 1. That will also be your horizontal asymptote. Plug in large values to see for yourself. And finally, if m is greater than n, there's no horizontal asymptotes. If you were plugging large values, you see that y keeps increasing. So we'll examine these two cases in a little more detail when we meet again during block 1. But just keep in mind that when you have case 1, horizontal asymptote is y equals 0. If the derivatives are the same, horizontal asymptote is y equals a over b. M is greater than n, there is no horizontal asymptote. So in essence, the horizontal asymptote tells us what y approaches when x approaches positive infinity or negative infinity. That means a more proper name for horizontal asymptote is end behavior asymptote. We've talked about end behavior before, like how the left and right ends behave. That's what the horizontal asymptote is telling us, like how the left end and right end of the graph will behave, where it will basically level off. So in case 1, it levels off at the x-axis for y equals 0. In case 2, it levels off at y equals a divided by b, the ratio of the leading coefficients. And for the third case, there is going to be no leveling off. Basically, y approaches infinity or negative infinity when x does the same thing. A more formal way to express end behavior asymptotes is the following. So these are called limits. And so if f of x is case number 1, when m is less than n, then it means that the y value is going to approach 0 when x is approaching infinity or x approaching negative infinity. If we have case 2, so that means that m equals n, the y values approach a over b when x gets really large or really small. So that's what happens to the y values. And lastly, if we have case 3, when m is larger than n, this will be a little tricky. But the because there's no horizontal asymptote, the y values approach infinity or negative infinity. In either case, it all depends actually on the sign of your leading coefficient, whether it's positive or negative. We'll talk about that in a little more detail when we meet during block 1. But that's a more formal way of writing it. And this might be a little confusing, but when we do some examples and you do some practice in class, will make a little more sense. So examples. Let's graph this one here. State the domain and range. So first step will be to find your asymptotes. So the VA real solution for this. So there's no VA. For the HA, we're going to say y equals 0. That's because m is less than n. M here is 0, n here is 2 because there's no x. So basically the degree is 0 for that function. And the bottom is 2. So step 2 now is to make a table. Now in this case, because we don't have a vertical asymptote, we really could just choose any x values we like say 0, 1, and -1. You get 6, 3, and 3. And after you make your table, let's graph it. So we know horizontal asymptote y equals 0. There's no vertical asymptote. 0, 6, so 1, 2, 3, 4, 5, 6. 1, 1. Plot your points. So the graph will look something kind of like this. And the reason why that's the case is because of the end behavior asymptotes. As x approaches positive infinity or negative infinity, y is basically approaching 0 because your horizontal asymptote. So we need to make sure they go against the asymptotes. That's basically how we graph it. Domain and range, I'm not going to ask. Actually, let's scratch that. Because these are going to be a little bit too tough to tell. You haven't learned enough material to be able to do that. So forget about domain range. Because you don't truly know how high it's going to go for most of these functions. This one's pretty obvious that the highest goes is 6, but you're not going to be able to figure that out until you get to calculus. So let's just scratch that. So that's how the graph looks. Okay, example 2. Step 1, find your asymptotes. So for the VA, again, set the denominator equal to 0. We talked about this today in class. So you get 2 vertical asymptotes. For the HA, if we think about it, m equals n, so y is equal to 2 over 1, or just 2. Because here m is 2, n is 2, and a equals 2 and b equals 1. So it's going to be the ratio of linear coefficients. Now step 2, we make a table. Before I make my table, let's plot the asymptotes. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have an asymptote here. We have an asymptote here. And I'm going to have an asymptote right here. So actually we have 6 regions. So what I want to do is pick an x value in each region. So I'm going to go with 4, 0, and -4. That's because -4 is to the left of my leftmost vertical asymptote, 0 is in between my two vertical asymptotes, and 4 is to the right of my rightmost vertical asymptote. If I plug in 4, I should get, I think, 4.6 if you work it out. It's kind of nasty. If you plug in negative 4, you should also get 4.6. And if we plug in 0, we should get 0. So here's 0. 4, 4.6, probably roughly over here. Negative 4, 4.6, and then 4, 4.6 right there. So now we know we'll have graphs like this. And the middle one's a little weird. But remember, the whole purpose of the asymptote is so that the graph goes against it. And so we have that. Again, a more proper way to do this is to make a sign chart. I'll do this in class during block 1 because this video is already getting kind of long. But that's what we have for our graph there. And then lastly, example 3. So, again, step 1. Find the VA. So x minus 2 equals 0. X equals 2. HA, there is none. Since m is greater than n. Because m equals 2 and n equals 1. Instead, there will be a slant asymptote. I'm actually going to show you how to find that in class tomorrow, just because that kind of takes a while. But it will involve, you guys will love this, long division. So I'll show you that on block 1. But I think we have enough to do this graph. Make a table. So let's plot 1 and 3. If you plot 1, you should get 0. If you plot 3, you should get 14. And the more I think about it, we're going to have to find the slant asymptote. So let's actually do it. So as I said again, you need to use long division. If you remember, you want to figure out how many times x goes in x squared. That's x times. Subtract. You have 5x minus 4. X goes into 5x 5 times. So we have that. So you have 5x minus 10. Then we could just kind of stop at that point. So x plus 5 is what we have here. So that's going to be your slant asymptote. So now we make the graph. Okay. So say this is 14. And we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I plot 1, 0. Plot 3, 14. Now if I graph my slant asymptote, it's actually going to look like this. And graph my vertical asymptote, it'll look like this. So graph will be kind of like that. And again, we're looking at how the ends of the graph behave. And so when x gets really, really big, if we were to work it out, essentially you start noticing that y follows this behavior of y equals x minus 5. Oh, sorry, x plus 5. 1x gets really, really big. So again, we'll kind of explore this when I see you guys in class, but it is a little bit tricky. But that's how essentially we want to go about this. So I'm all done for today. There's some problems I'll have you try at home, and then we'll discuss in class when I see you later. Goodbye.